So it's my pleasure to welcome you to this conference, which is actually, we have two conferences happening at the same week. A conference organized by Mathematicians, myself and Bernd Hofmann, and another conference organized by our colleague engineers, Marcelo and Elcio. And so the talks will be interchanged between these two communities. I hope you enjoy. This is it. So now I will let Elcio introduce the first speaker. Please, Elcio.
Okay. Well, good morning, all. I'd like to say that it's a great pleasure to be here, being invited by Antonio Leitao and Bernd Hofmann to help to organize this conference together with Marcelo Colaco also. And I think that these are two conferences inside one single conference. So I think that mixing the talks between mathematicians and engineers, I think it will be very nice to cross ideas and bring new applications for algorithms and for techniques that are being developed. And from our side, I think that we profit a lot from this, and I hope that we have a very profitable weekend with fertilization of ideas. It's a great pleasure for me to introduce the first speaker, Professor George Dulikravich, who is a very good friend. And talking about this, in the engineering community, he's the one who started the conferences on inverse problems. In 1984, he started the first conference on, it was called the ECIDS. And in engineering, we have two conferences that, like the International Conference on Inverse Problems in Engineering. The first one was in 1993. And George Dulikravich and I and Marcelo, we started a series of conferences also called IPDO, Inverse Problems, Design and Optimization Symposium. And we have had a lot of mathematicians coming to the conference, but I think that it really never it started a full cooperation between the two groups, which I expected that we can start here. And George Dulikravich, he's a very well-known person. He has many awards from different parts of this world, many countries, and he is a full professor in the Florida International University, where he leads a big group related to inverse problems, design and optimization. And he's the co-founder and the editor-in-chief of the journal Inverse Problems in Science and Engineering. So without taking too much longer time, I'd like to pass the floor to invite the George Dulikravich for the floor for his talk. Thank you very much, George. Thank you.
Thank you. Appreciate it. Thank you very much. Good morning. Everyone can hear me well? You back, Alice? Good. Thank you. I will try not to yell. I usually don't use microphone, but since you're quite far away, I will try to use microphone. Let me see if I know how to use this. Good. I'm currently working at this university, which has about 55,000 students. It's located in Miami, and it's the largest Hispanic minority institution in the United States. As far as number of degrees granted, it was the largest one compared to the others. Objectives of this presentation are basically how to demonstrate, use a very simple approach to very diverse types of inverse problems. I'm going to minimize any mathematics. I'll leave it to mathematicians. Engineers like to go down to the actual application. So the concept is exceptionally simple. It deals with establishing an L2 norm between the measured quantities and the predicted quantities that are a result of the guessed values of the unknown parameters. And of course, then minimizing this L2 norm. and a number of different minimization algorithms to perform this. I will here focus on one algorithm which works. It's called, basically, we started this in my group in 1999, referred to as a hybrid single objective optimization algorithm. Since then, it has evolved significantly. So obviously, this entire approach has certain advantages. The advantage is that it can be used by people that are not really good at mathematics, and this means engineers. It also is good. The benefit is also that it requires minimum or no modification to the analysis code or analysis methodology. And of course, it is highly flexible. So it can be, as I mentioned, used in a number of different disciplines. Here's an example of something that looks like a nice convex shaped domain. And of course, it's known as Grievang's function after Andreas Grievang in Dresden nowadays. But basically, so one would think, yes, this is very easy to find whichever initial guess we choose for the value of this objective function by varying x and y, just two design variables, how to find the global minimum of this function. However, if you blow up this inner region here, we see that actually it is not very smooth. If you further extract one section of it and really blow it up, then we see we have a huge number of local minima. So any classical gradient-based optimization algorithm, for which you have all sorts of proofs, how well they converge, under what conditions, and theories, and lemmas, and proofs, and corollaries, okay? They're all going to fail here because they're all going to, whatever initial guess is, they're all going to basically slide down the steepest gradient, steepest descent, and terminate in the local minimum without any ability to climb up again and keep on hopping over different hills until they find the global minimum. So industry does not use gradient-based optimization or minimization algorithms anymore. This is an example of what other algorithms are doing. The best, the most accurate, the most efficient gradient-based algorithm. These are just the initials of the names of people that published the original version. You can see in the case of Grievang's function, which you saw visually a moment ago, that this is the error, which should be, of course, going down to machine accuracy. As the iterations proceed, the process of convergence is extremely slow, and eventually the whole thing just ends up in a local minimum. Differential evolution, which is an improvement of a genetic algorithm, so it is non-gradient-based algorithm, excuse me, is still trying to find the right button, is also having a very slow convergence in this case. So it doesn't sit in local minima, but it sits there for a while until eventually digs itself out, okay, using a random redistribution of the search parameters. The simulated annealing, according to textbooks, is the fantastic algorithm that is absolutely capable of digging us out of a local minimum, although it's going to be painful. Well, it doesn't look it's working. Particle swarm algorithm, which is the most commonly used nowadays, a non-gradient-based minimization algorithm, also has a problem of eventually getting locked in a local minimum. However, hybrid optimizer keeps on converging down to the global minimum. Okay? So what is the feature of this hybrid optimizer? This is the first one, which was developed, let's say, in 1999. Since then, about 8 generations have been developed with this hybrid optimizer. And this one involved a collection of the constituent algorithms, in this case, genetic algorithms, simulated annealing, simplex, basically Nelda-Mead, modified Nelda-Mead, differential evolution, and of course, David and Fletcher Powell sequential quadratic programming gradient search, and modified Newtonian, quasi-Newtonian Pшеничный annealing algorithm. Each of them are very powerful on certain classes of problems. But each of them, as you have seen, fails miserably on even a nice classical example of a multiple minima problems. So if you have whole collection of algorithms, some of them non-gradient based, some of them gradient based, and if you develop control algorithm which automatically switches among them each time when certain criteria is met in the iterative process, sketched here, then you can see that we can basically keep on bouncing between, say, differential evolution and genetic algorithm, or between the Davidson-Fletcher-Powell gradient method and the differential evolution method, okay, and so on, whenever each of these criteria are met. And they are described in these publications from 18 years ago. Since then, as I mentioned, the entire algorithm was further simplified by reducing from 6 constituent algorithms to only 4 constituent algorithms. This one worked better. And eventually nowadays, the latest version is the one which has a sort of particle swarm algorithm with Boltzmann probability, and then the best gradient-based algorithm, and a certain version of differential evolution. Okay? And this one is, as I said, the most recent one we've been using for the past about 5 years. Professor Colaco is one of the co-authors, and he had been working heavily in these things. So this is my little story about hybrid optimization algorithms. Okay? Nothing new about each of the constituent algorithms. It is only novelty in how to create automatic switching among them. And they can switch back and forth, okay, between 2 algorithms, okay, if necessary. So here's one example of classical problem of elliptic partial differential equation of steady heat conduction, where the temperature, the thermal conductivity of the isotropic material is dependent on temperature. And there are a number of ways how to handle this. And the simplest probably way, and we still believe probably most appropriate way, is to use Kirchhoff's transformation to convert from the temperature to this temperature function, let's call it U, so that this equation becomes just a good old Laplace equation. And we did it because once has a Laplace equation, of course, we can use very simple and appropriate algorithms to integrate this equation. So we used the boundary element method on this, okay, and basically iteratively solve this. In the process, which is outlined here, of course, we used a certain linear combination of these basis functions, okay? And here's the final story. The resulting system, of course, was cast in the following covariance matrix form and so on. So, of course, the only, it's not really a challenge, but the variety of options for what to choose the basic functions, and we tried a number of them. The standard polynomial, Chebyshev polynomial, third order beta splines, and so on. And basically, I'm going to show you what kind of results we're getting. So in this case, this is temperature, and this is thermal conductivity that was determined from this procedure, with a number of different of these basis functions that we used. And you can see they all are giving us analytical solution is, of course, the straight line. So they all gave pretty much good, very good prediction of the temperature dependence of thermal conductivity, except the L2 beta spline approach. And here, combination of showing the similar behavior when working with the other basis functions. And of course, working in the case of no error in the measurements of the temperature on the boundary. By the way, I forgot to mention, we have to measure temperatures on the boundaries, right? So we have to have a boundary conditions, Dirichlet boundary conditions in this case. So assuming there is 0 error in these Dirichlet boundary conditions, then of course we are getting A solutions, okay? Then sigma is like 0.1 degrees Celsius, we're getting this, and we're getting further like with this 1 degree Celsius or with this 5 degrees Celsius, which obviously over the range of this means 5% basic error. This is huge error, because most of the measurement devices for measuring temperature are having maximum error of approximately 1%. So we are really exploring something that is not even relevant. I mean, such a large error, right? And it works, oh yes, and then we also did some of the perturbations, not just to the Dirichlet boundary conditions, but in the case that we measured also temperatures and we measured also heat fluxes. So there could be also error in the heat flux measurements. Okay? So if you introduce these errors in heat flux measurements, then we're going to get a little bit more of a error in the predicting the thermal conductivities, but still quite a decent result. And of course, here is the example when the temperature dependency, well, thermal conductivity dependency on temperature is not linear, but it is highly nonlinear, okay? Almost like two materials meeting each other. Okay? So it is of the type of the arctangent function. And you can see that most of these methods are giving very nice results, except when you start introducing simulated errors, in this case of temperature, measure temperature on the boundaries. Okay? And you can see that in this case, of course, we are starting to develop certain errors in the prediction. And these errors are growing as the relative errors in the boundary measurements are growing. Okay? Here is an example of the actual copper. Copper is highly nonlinear thermal conductivity in an extremely low temperature range. Most of the techniques nowadays are capable only predicting one single constant value of thermal conductivity, or at most linear variation. This one, as you've seen, can predict a highly nonlinear variation of the thermal conductivity. And again, with a number of different basis functions, okay? And different levels of the errors in the boundary measurements of the temperature. And this, of course, can be applied to any object. So you don't have to cut everything to be a nice rectangular region, sample, and thus everything is nice. No, it can be completely arbitrary object. In this case, actually, we did the multiply connected object. So this is like a circular plate with a hole in the middle and a handle here. And these are the resulting isotherms inside. This black line is error from the plotter, so don't pay attention to it. And you can see here that by taking just one temperature probe and measuring temperature at a bunch of locations and also inside on the boundaries, and taking just one heat flux probe, so one Dirichlet boundary condition measurement probe, one Neumann boundary condition measurement probe, we can input these measurements into the code, and the code very rapidly actually gives us this prediction of the thermal conductivity coefficient as a function of temperature. So it's very nice quality prediction. Here's another one, also from a heat transfer, but in this case, heat and mass transfer. So say that you have chips, potato chips. Okay, drying potato chips in some factory produces potato chips. And this potato chips are on a conveyor belt. And conveyor belt is heated from below. Okay, so we have constant heat flux coming in. And here's a hot air with certain humidity and temperature blowing at uniform speed along the top surface. So this is a relatively thin layer. And here are the typical governing equations for this. Temperature, and here's moisture content. And of course, boundary conditions themselves also involve something dealing with the mass transfer and moisture transfer. So the question is that we are going to have here a number of parameters that we really don't know what they are, okay? But we can measure. We can measure what? We can measure, say, temperature at a point, okay? So for example, we don't know diffusion coefficient in this situation. Okay, we have no clue, okay? And a bunch of other parameters. The variation of density with time, for example, of the solid part, and so on. So here are some of the remaining explanations. So this is basically convective heat flux and mass flux, the water vapor concentration in the drying area given, And eventually, again, we are just forming the L2 norm we are trying to minimize. Okay? So this vector of the unknown parameters, in the case of convective drying, is going to involve all of these unknown parameters. Okay? So the entire process is quite involved physically, but really could be solved relatively easily using very standard minimization algorithms. And in this case, again, just forming we use the Lemmenberg-Marquardt method, which we abandoned afterwards because this method is a gradient-based method, which means that the initial guess, the final solution is going to depend on initial guess. Okay? So we can easily end up in local minimum and end up with the wrong prediction of these coefficients. Afterwards, we switched again to our hybrid optimizer. But I'm just going to point out that in this case, of course, we have to determine the sensitivity coefficients for each of these unknown parameters, okay, as a function of time during the drying process. And here's some of the results. So you can see the moisture in this. This is over the thickness of the entire, this one horizontal, which should be on the vertical. Moisture variation is significantly varying in time also. So initially, of course, it is very high, but then it's dropping down quite rapidly as the time progresses. Okay? And then eventually moisture goes almost uniformly to zero at the end. Okay? Similarly, temperature with the time is going to progress from a certain low value to high value, which is basically temperature of the blowing air, which is above the thing, the chip. And here the eventual numbers. So exact values of these parameters that are simultaneously determined. Initial guesses for these. So you can see that basically these are very different numbers. Excuse me. And of course, estimated values with the assumed 0% error in the measurement. And then with errors which are sigma is 0.5, even when some of them are not being determined. So we are saying in this case determine only 5 instead of whatever 7 parameters. In this case, you determine all 7 simultaneously. So the method works very nicely for a number of a disparate type of parameters. In this case, of course, each of them is treated here as a constant. So these are unknown constant parameters. This is an example from solid mechanics. In this case, we have a simple classical Mindling plate. Okay? So a Mindling plate is just given here, 2 dimensions, and he's clamped here and clamped on this wall. And of course, he is free. He is loaded with concentrated force and also loaded concentrated force. So there will be certain deformations and distribution of stresses. If you're trying to analyze this distribution of stresses and deformations, we need to know Young's modulus of elasticity. But we pretend that we do not know what is the Young's modulus of elasticity. Moreover, we do not know if it maybe is varying in space. Okay? So it might be varying in x and y direction, but we don't know it. So based on our measurements of stresses, deformations, and so on, could we determine the spatial distribution of Young's modulus of elasticity? So 2 approaches to this. One is to pick any finite element. This is done with finite elements. Could be done with other techniques. Say finite element, pick up certain finite element which has corner grid points which are the most sensitive, if you wish, to the variation in the loads. And the other approach was to measure the forces and moments on the clamps boundaries. Okay? So let's see what kind of results we're going to get from these 2 approaches. This is just a complete 3-dimensional thermoelasticity formulation. So we have a system of partial differential equations. But in this case, there was no temperature. So obviously, we're going to drop anything that has to do with temperature. And this means these x, y, and z, which are due to the temperature variations. So we don't see them in our application. And of course, it's 2-dimensional. So it's going to be just basically 2 coupled partial differential equations. Okay? And of course, we know classical relations, Young's modulus of elasticity, Poisson ratio nu, And then we have, of course, lambda, which are lambda coefficients. So E modulus elasticity will be treated as spatially varying. How? How does it vary spatially? Well, we will have to specify certain mathematical functional relationship between E and the location. So let's say we're going to use a second order simple algebraic expression. So if modulus elasticity varies as certain coefficients times x squared plus some other coefficients of y squared and so on, then these four coefficients, E1, E2, E3, E4, are unknowns. If I can determine them somehow, I will have a proper variation of modulus elasticity in this plate. So the first approach was, of course, I'm going to measure, as I said, I'm going to guess the values of these four coefficients. I'm going to analyze the entire distribution of stresses and deformations. And then I'm going to take the difference between a measured and the predicted values and minimize the normalized L2 norm of some of these differences. So first approach is initially we guessed that the values of these four coefficients are all 5 megapascals. The correct values were 2, 3, 6, and 8 pascals. Okay? After 2,000 iterations, remember we picked one element, and basically on this element we made this, create this function which we were minimizing inside the domain. The error was still 30%. So this is what we should have been looking for, distribution of modulus elasticity. This is what we obtained. I mean, there is no comparison, absolutely. Okay? And of course, numbers are completely wrong. So this is not a good idea. Let's not dig into the domain. Let's measure things on the boundary. Okay? So we took measurements on the reaction force, and moments on the climate boundaries. We started with the same initial guesses using hybrid optimizer. This is what we should have obtained. This is what we did obtain. Okay? This is very close. The maximum error is less than 2%. Okay? And this is after just 100 iterations. So remember, we should have received correct values at 2 megapascals, 3 megapascals, 6 megapascals, and 8 megapascals. Okay? So obviously, it worked very nicely, and it was on a quite coarse finite element grid. This is one practical application. There are many applications in real engineering where people are starting to use porous materials, metallic materials, in this case, tubes filled with the metallic foam, okay? Because this can absorb large amount of energy in order to be deformed. So car and automotive industry, aerospace industry like this kind of approach. And of course, there is a difference if you are going to test this on bending, for example, bending this kind of machine parts, whatever. If you're doing it statically or you're doing kind of rapidly, dynamic loading, okay, there's going to be some difference. But in both cases, the variation is not just stress and deformation, it's not linear. So stress and deformations are related also non-linearly. So deformations are plastic. Well, they're plastic, then obviously typical way is to use, again, software which is available for analysis of the elasticity problems and then vary sequentially local modulus of elasticity. But what are the values of local modulus of elasticity? We don't know. And also very locally Poisson's ratio, which we, again, do not know. Okay? So in other words, this is quite an interesting problem. And here's some of the classical solid mechanics approach, formulation. And here basically some of the attempts how to do it. This is quite recent. This was done about 2 years ago. And it can be used with the Bayesian techniques and finite elements. The entire solution process would take of the order of 1 month. It can be repeated with the Bayesian techniques, but using radial basis functions for the response surface interpolation. This would take maybe 1 hour. Or it can be brute force solved using hybrid optimization and the radial basis functions. It takes 5 minutes. So you can see the benefit of sometimes using not all that fancy mathematical approaches and getting useful results. Okay. And here you can see basically the results from the optimization and from the Monte Carlo techniques. And of course here the calculated values of a Poisson's ratio, Young's modulus, and the sequential values of these. So here is just a plot of such a variation of the force versus displacement, experimental values are crosses, and then red values are simulated. And of course, with 99% of the confidence interval, this is obtained using Bayesian techniques. And this is basically very, very similar accuracy obtained with the hybrid optimization, just minimizing the L to norm difference. Here's an example in heat transfer, again. But this case, the thermal conductivity is not function of temperature. No, it's function of space. There are not too many applications, there are not too many publications handling this kind of problem. There are quite a few publications out there that are handling thermal conductivity as a function of temperature, or the function itself. But no, here it's thermal conductivity function of space. Okay? So how can we find out variation in space of thermal conductivity just based on the boundary condition measurements of, say, temperature, okay? Or boundary condition measurements of heat fluxes. Okay? So in this case, we are going to again assume one pretty nasty looking variation of the thermal conductivity with certain coefficients which we do not know. K minimum, K maximum value, coefficient A, coefficient B, and these exponents C and D, or the sign functions. So if we plot this in such a rectangular test domain, we're going to see this analytical representation of thermal conductivity varies quite dramatically, okay, in certain regions. This here is predicted using, again, now analysis software such as COMSOL or ANSYS Fluent, combined with our hybrid optimizer. And you can see the difference is almost negligible. Okay? And then corresponding final from these predicted values of the distribution of the thermal conductivity, comparison of the analytic value of the temperature distribution and the computed value of temperature distribution. Here's another example of a similar thing, but now in this multiply connected domain. So here again, thermal conductivity is given with a basically very similar function, but here it varies at the sine wave multiplied also tangent or arctangent wave. Okay? So we have again a bunch of A, B, C, whatever coefficients and these exponents here that we don't know, K min, K max, and you can see distribution of the thermal conductivity according to the assumed analytical function distribution and assumed values of these coefficients. And here, of course, we can see it with the, in this case, with the zero error in the boundary measurements of temperature, and here with the boundary measures of temperatures up to 5%, which is huge. Okay? And of course, here is just the error itself, location of the error, all the way up to 10% if there is error in boundary condition measurements of temperature, how it is going to result in the errors of distribution of predicted value of thermal conductivity. Okay. Finally, it just happened out to be maximum error here, but still extremely low. Okay. Here's in the three-dimensional version of it. So you created an axisymmetric version of it, like here, with these kind of wormholes inside. And on the surface of each of these, we have different heat fluxes prescribed, or different temperatures and so on. Based on these measurements, computationally simulated measurements, assuming this analytical formulation for distribution in 3 dimensions of the thermal conductivity, we determined, again, minimum, maximum value of coefficients, and then coefficients A, B, C, D, E, and F. Okay. And here they are. So you have boundary conditions. Here, the analytical values of each of these, whatever, 8, 9 unknown parameters. These are predicted values using optimization. maximum error is 10 to the minus 8th. If there's 1% error in the Dirichlet boundary conditions, measured temperatures on each of these boundaries, the error grows to 10 to the minus 6th. And if the error in the measurements grows up to 3%, where the set is way beyond and more than typical measurement errors obtained from the nowadays temperature measuring devices, then of course the Jacobian value, the error, is growing up to about 10.9. But again, you see how accurate these predictions are, even with very large measurement errors. This is quite remarkable, okay? And it's a very fast process, of course. How much time do you have? 5 minutes, okay. Oh my God, including questions. Let me skip this. So this is a repetition of this now with the unsteady problem, where we basically did distribution simultaneously of specific heat and thermal conductivity. Works fine, believe me. Magnetized fiber orientations. Oh, by the way, here is the history of the cost function, and here's the iteration number with the optimizer. And you can see these are different constitutive optimization algorithms, okay? And how it is switching from one to the other each time when certain criteria is met, okay? Electromagnetics. Here is the last one, and here's the example of infectious diseases. So in this case, it was example of syphilis, because we just collaborated with one person who is expert in infectious diseases. And this person had data, actual data from 1900 all the way to 1970 for the mortality per 100,000 inhabitants of each age, person, from infants, 1 year and less old, all the way to 85 plus years old. So we extracted mortality of these infants, okay, which were the red, so this red curve here. And we are trying now to develop some sort of algorithm that is going to be able to predict this, and then hopefully predict what is in the future if this is, what's going to be the situation. So it ended up that this is a scheme, and you can see that there are many possibilities of being infected, being partially cured, being reinfected, even tertiary infection, and latent infection. I mean, babies can be born with the syphilis because they inherited from their mothers during the birth. Okay? So in this case, the model developed by that person we collaborate with is a set of 10 ordinary differential equations. So the highly coupled 10 ordinary differential equations, but they have a whole bunch of coefficients inside which nobody has a clue what they are, what their value should be. So there are 24 unknown coefficients. They're listed here. They know roughly what should be the minimum values for each of them, what should be roughly, what should be maximum values for this. So nobody knows exactly what they should be. So Lloyd said, oh, what the heck? Let's just try average value between minimum and maximum for each of these 24 coefficients. And let's run this system of 10 ordinary differential equations with these average value of these unknown coefficients. Here's the result. So we predicted that there will be 14,000 deaths, okay, per year maximum, while the number actually is 120. We took in 2 orders of magnitude error by using just the average value of these coefficients. So obviously it is total nonsense. Okay? Don't use average values. Okay? How about it? And then running through our procedure again, we found the optimum values of these coefficients and even analytical relation between 2 of them, so it turned out to 23 unknown parameters. And here are our predictions compared to the blue line, which is the actual historical data. Here again, we originally assumed certain things for the population growth, a sexually active population, and interpolated locally with certain functions. And here's the eventual. We even allowed some of these coefficients to vary in time at third-order polynomials. And here you can see comparison of different approaches. So this was if you use the average value, which is completely wrong results. Here, if you find out what these actual coefficients are, in this case, 23 coefficients. Of course, we are forcing our model onto the actual situation. So this is a big, big misgiving for all the inverse problems. If you're trying to force data to fit the model, okay, rather than forcing model to fit the data. And of course, here in a summary, the positive values, positive things about this approach of using hybrid optimization is that it works on a number of different applications for single and systems of PDEs and ODEs. It can work in 2D, 3D domains, multiplicative domains, fine. Negative thing is optimization, minimization algorithms must be very robust, must be very accurate and versatile, or they will converge prematurely. They'll converge to local minimum. Okay? And when using response surfaces to speed up the whole thing, multidimensional interpolations, accuracy of the response surface must be high to avoid errors in the final results. And of course, spatial variation of the unknown parameters must be assumed. That's the big drawback. We have to still assume the functional variation in space. Okay? So I'm just leaving this an open question, how to estimate an arbitrary spatial distribution of an unknown parameter. Thank you very much.
Thank you very much, Professor Dulikravich, for this very interesting presentation. Have time for questions.
Thank you for the very nice talk. So in the very last slide on the evolution of the epidemiological problem, yes, right there. There is, in all graphs, you see some kind of break around 45 or so, 1945. I was wondering if there is some kind of change in the dynamics, because you see in all these graphs different behavior, perhaps antibiotics or something like that.
Why is it dropping off?
Yes, yes. Yeah, antibiotics, yeah. Okay, thank you, yeah. Yes.
Questions? Okay. Okay, so let's thank Professor Dulikravich again. Thank you. Thank you.